All right, so our next lesson is going to look at sections 5.2 and 5.3. Although they are distinct topics within the book, I present them really as one large topic because I think it makes more sense to do some of these things together, right? So within this next video, there really is no delineation in terms of where 5.2 and 5.3, it's all kind of mixed together in a way that I think makes the most sense. So let's first start with the definition of a polynomial. This is a very formal definition, but a polynomial function of degree n, right, in the variable x is a function defined by p of x equals a sub n times x to the nth plus a sub n minus 1, x to the n minus 1, plus so on and so forth, all the way until we get to a sub 1, x to the first power, and a sub 0 or a naught, which is our constant term. All this means, okay, don't get caught up in the fancy superscripts and subscripts. All this means is that if I start, say, with a 5th degree term, my next term is going to be some a times a 4th degree term, and then a 3rd degree term, so on and so forth, all the way down until I get to that 1st degree and the constant term. Okay, so all it's doing is saying I'm decreasing power, and these subscripts are just identifying a constant that goes with a specific variable. Okay, a little bit of terminology. A sub n is referred to as the leading coefficient, right? A sub n x to the nth is sometimes called the dominating term or the leading term. Okay. A naught or a sub 0 is our constant term. It's the one where, and really I have a sub 0 x to the 0 power, but x to the 0 is simply 1, therefore we just have our constant. Okay. And then the last but not least, assuming I have a polynomial in standard form, right, so it's all multiplied out in decreasing order, then p of 0 is a naught, is the y-intercept of the graph. So the point 0, a naught, is going to be on my graph, right? Am I ever going to ask you to recite this? Absolutely not, okay? But it is going to be important for you to understand some of the terminology that's in here, but I will never ask you to recite or write back the actual definition of a polynomial word for word. So let's talk about degree of a polynomial. All right, so the degree of a polynomial is essentially the degree or the highest degree of all of its terms. So what's the highest power? Okay, so if it's in standard form, it's nice and easy. So here f of x equals 3x to the 4th minus 2x squared plus x plus 14. My largest exponent here is a 4, right? So this is 4th degree. Okay. In example 2, g of x, I have g of x equals x cubed plus 5x squared plus 4x minus 1. Again, I'm looking at my highest degree term. Right? Here it's a 3, so I have a 3rd degree term. Now where it gets tricky is if I have something that is in a factored form. Now what I need to do, and keep in mind if I have individual terms, all right, so let's say I had like a to the 4th times a to the 5th, right? When I multiply like bases, I add those exponents. So here I get a to the 9th, right? Same kind of thing is going to happen here, right? If you take a look, I have x times the quantity x plus 3 cubed times quantity x minus 2 squared times x squared plus 1. This x to the 1st, or x, is an x to the 1st. Okay, so what I need to look at is the degrees of each of my individual terms, right? You don't need to write this out, but think of it as if this were an a to the 1st times an a to the 3rd times an a to the 2nd, and the degree of this last term is also a to the 2nd. If I were to multiply that together, I'm going to add all of those exponents, and the sum of the exponents is going to be the x, or the new exponent for that product. The same thing here. All right, if I have something in factored form, the sum of my individual degrees, right? If I multiply them out, the leading terms would have to be essentially the degree of each individual quantity, right? And when I multiply them out, if you were to do this, this would take you quite a while. You're going to end up finding that in this case, our sum is going to be 8. This would be an 8th degree polynomial. So again, if you have something in standard form, we're looking for the highest exponent, all right? If we have something in a factored form, then I need to look at the product. And again, think of the exponent rules, right? If I were to multiply that out, what's the sum of my exponents? What's the sum of the degrees of each individual factor, okay? Let's talk about multiplicities, okay? Multiplicities don't necessarily have anything to do with degree. What multiplicities deal with is for each solution that we get for a particular polynomial, we're looking at how many times does that particular solution occur, or does that same solution occur. And based on that, it tells me what happens to the graph at that point, right? It doesn't matter what the solution is, whether the solution's even, whether the solution's odd, right? It matters whether the multiplicity is even or odd. So let's go through this. So if C is a 0, so if I have x equals 0, or x equals C rather, is a solution or a 0 of a function f with multiplicity m, then the shape of the graph of f near the x-intercept or the 0 or the solution C is as follows. So if my multiplicity is odd, okay, then we're going to cross the graph. So at that point, I'm going to go from below to above or above to below, okay? So again, if my multiplicity is odd, my graph is going to cross the x-axis at that particular x-intercept, okay? If the multiplicity is even, my graph is going to touch but not cross the axis. So it's going to come from one direction, touch, and then go back in the direction that it came from, okay? Again, it doesn't matter what the actual solution is, okay? The solution itself can be even, odd, rational, irrational, all right? Doesn't matter, okay, as long as it's a real number. I need to know the countable, how many times does that solution occur, right? That cardinal value, does it occur 1 time, 2 times, 3 times, 18 times, right? If the number of times that it occurs is odd, we cross. If the number of times that it occurs is even, we touch, okay? End behavior of polynomials, all right? So given a polynomial, the end behavior of that polynomial, what happens where your arrows go off in 2 different directions, all right, on the left and right hand side of our graph, is going to be determined by the degree of the polynomial and the sign of the a sub n term, whether it's positive or negative, okay? So if I have an a that is positive and a degree that is odd, I'm going to have a graph that behaves, right, and think x cubed, right, where it's going to go in opposite directions, okay, on each endpoint. If a is positive, right, on the left, that graph is going to have an end behavior that is down, and on the right, it's going to be going up, right? If a is negative, if a is less than 0, then we're going to have an end behavior that on the left is going up and on the right is going down. It's going to now look like a negative x squared, right? So again, if a excuse me, is positive, think y equals x cubed. If a is negative, think y equals negative x cubed. Now, the thing that's important here is it tells me what's happening for those tails or the ends where I've highlighted. I have absolutely no idea what's happening in the middle based on simply end behavior, okay? That's where my information about solutions or zeros and the multiplicities comes into play, and allows me then to figure out what's happening or get an idea what's happening in the middle of the graph, if you will, all right? If I have an end behavior, or if I have rather a degree that is even and an a value that is greater than 0 or is positive, I'm going to have you think y equals x squared, right? Parabola, my two ends are going to go in the same direction, right? And if that were the case, on the left, it's going to be going up, and on the right, it's going to be going up, okay? If we have a value that is negative, then you're going to think y equals the opposite of x squared. It's going to flip upside down, and on the left and right, both endpoints are going to be going in the downward direction. Okay, again, end behavior doesn't tell me what happens at either or any of these intercepts. It just tells me what's happening on the end, essentially as my x values go toward positive and negative infinity. Okay. Intercepts and turning points, so everything we're dealing with, at least for the moment, when we're dealing with polynomial functions, should be continuous functions, all right? If we're not dealing with, or if we're dealing with something that's not continuous, where we have discontinuities, whether it be from division by 0, or, square roots and negatives, so on and so forth, then this doesn't really work. This is for polynomial functions. So, assuming and polynomial functions are continuous, meaning that I can essentially draw the entire graph. I can put my pencil down and I can draw the entire graph through to the other end without ever lifting up my pencil. There are no breaks in the graph, okay? And I can do so with a smooth curve. There's going to be no abrupt changes in direction. I mean, there might be curves that happen quickly, but there are no abrupt changes. There are no sharp points, if you will. All right, so if I have a polynomial of degree n, I can have at most n minus 1 turning points. Okay, so if I have, for example, think about it, a parabola, right? Quadratic. We know what that has to look like, right? So if I have a parabola, my endpoints have to go in the same direction, whether it's both up or both down. If I start from left to right, and the graph is coming down, I can have one turning point here at the bottom at the vertex, where my graph goes from decreasing to increasing, right? The only turning point I can have occurs right there, right? So degree 2, I could only have one turning point. If I have another turning point, now all of a sudden, I have something that no longer looks like a parabola, okay? Now I have something that has to at least be a third degree term, okay? Or a third degree polynomial, all right? So if we're looking at the graph that's here, right, I know that it at least has to be then a third degree polynomial because I have 1, 2 turning points. Okay, 2 turning points, it has to at least be third degree. My tails go in opposite directions, so it has to be odd. It could, however, also be a 5th degree or a 7th degree polynomial. Those are possibilities. Okay, it just guarantees that I at least must have a third degree polynomial here. Okay, and again, a turning point is where the graph goes from increasing to decreasing or vice versa. Yeah, I don't think we need to talk about the y-intercept. You guys know what that is. All right, so just real quick, polynomial functions and end behavior, okay? Here I've got 5x to the 4th plus 2x cubed minus x minus 4, right? This actually gives me a graph that looks something like this, right? And in this graph, right, my end behaviors, as I would expect, the degree is even and a was positive, right? So my end behaviors are both up, right? Same direction, even. A was positive, so both up. All right, here I really only have, at least from what I can tell from the graph, one turning point, right? Again, 4th degree, I know I can have at most 3. I'm allowed to have less than that, okay? Second example, I have negative 6x cubed plus 7x squared plus 3x plus 1. So degree is 3, and a is negative. So I know then that my end behavior has to be up and down. All right, and again, our graph is exactly what we get here. I get an end behavior that is up and down, right? We'll notice that we have 2 turning points here. Again, that's allowable because we had a 3rd degree polynomial, right? And if I sketch the same thing in, my end behavior here, right, degree was 4, a was positive, so my end behavior had to be up and up, Okay. Next example, I have 3x to the fifth minus 4x to the fourth plus 2x squared plus 1. All right, so my lead term here is 3x to the fifth. It's in standard form. So I have a fifth degree polynomial. A is positive. So my end behavior, think x cubed, has to be down and up. And again, that's what we see here, right? I have a graph that comes up, turns relatively quickly, and it has a slightly smoother curve when it turns back into the upward direction. All right, and I do again here get a graph that is down and up. All right, you'll also notice that my y-intercept on this one was my constant term. It was 1. All right, we had the same thing here for the others as well. I just didn't point it out. Right, my y-intercepts matched that constant term of the function. Okay, last but not least, then I have negative 2x to the sixth minus 5, or x to the fifth rather, plus 3x to the fourth plus x cubed. My leading term is negative 2x to the sixth, right? So my degree is 6. A is less than 0. And again, so then I want to think negative x squared. Both endpoints or both tails need to be in the downward direction, right? So we're going to end up with a graph that looks something like this one. Okay, you'll notice that really here I have a plus 0 constant. All right, that there is no constant, so I'm going to have a y-intercept at 0. All right, if I don't have a constant, it also tells me that I'm going to at least have a GCF that's going to contain a 0. So here I have an x cubed term, so I could factor that x cubed out, and it would leave me with negative 2x cubed minus x squared plus 3x plus 1. Right, this would give me that solution of x to the 0 with a multiplicity of 3 because, right, since it's x to the third, really this is x times x times x, so I get x equals 0 3 times, right? I don't have to write it 3 times. Instead of writing it 3 times, though, I can simply write it just this one time and list it with a multiplicity of 3 to show that I do in fact have that multiplicity of 3, or 3 solutions of x equals 0. Okay, so I just wanted to quickly point out where I had a good opportunity. The solutions, point out a common mistake. People will drop that GCF out, and also where that multiplicity is coming from. The multiplicity is coming from the factor or the exponent of the individual factor that gives me the solution. Okay, we're going to look more at some of this here in a couple of seconds. So, without further ado, we're going to find some multiplicities here. All right, so I want to find all the zeros or solutions of the polynomial. I want to state the multiplicity of each 0. I'm going to find a y-intercept, and then we're going to sketch the graph. And again, we're going to sketch it because we don't necessarily at this level have the tools that we need to figure out all of the details of this graph. Okay, so we can get a good picture. We know what's happening at each intercept. We know what the endpoints are going to look like. But between intercepts, I don't necessarily know 100% sure what's actually happening. So I'm going to give my best guess and try and make it look essentially believable. Okay. Here, this is nice. It's already set in a factored form. So I can set each factor that contains a variable equal to 0. So here I'm going to get x minus 2 equal to 0, x minus 3 equal to 0, and x plus 1 equal to 0. And when I solve, I'm going to get x equals 2, x equals 3, and x equals negative 1. Now, if you'll notice, right, each of my factors here has a multiplicity, right? Where it's not written, it's assumed to be 1. So the exponent of each factor gives me the multiplicity. So for x minus 2 or x equals 2, I have a multiplicity of 1. For x equals 3, I have a multiplicity of 3. And for x equals negative 1, that solution occurs 2 times, or a multiplicity of 2. Again, anywhere where the multiplicity was odd, I cross. Anywhere where the multiplicity was even, I touch. Okay? I also want to identify the degree of the function. In this case, when it's factored form, I sum the exponents, I'm going to get 6th degree. My a value is this quantity out in front. If there's nothing written there, then it's assumed to be positive 1. Okay, my A value is greater than 0, so my end behavior is going to be even function A positive, so both tails or ends are going to be going in the positive upward direction. Okay. That being said then, the only other thing I need to do is find my y-intercept. Okay, a couple ways I could go about that. I could multiply this whole thing out and look for that constant term. It's going to be a lot of work. Let's not do that to ourselves. Instead, let's just evaluate f of 0. So if I do that, I have 1/25th, right, times x, or 0 minus 2, or negative 2, times 0 minus 3, or negative 3 cubed, and 0 plus 1 squared, or 1 squared. So if I do a little bit more simplification, I have 1/25 times negative 2 times negative 27, right? Or, excuse me, we're going to have 54/25ths, right? So 54/25ths is going to be a little bit larger than 2. So I know that I'm going to have a y-intercept somewhere right about here. Okay, I want to go through then and I want to actually plot each of my x-intercepts as well. Okay, so we're going to have an x-intercept at -1, right? And I'm going to put a t right here. All right, I'm going to have an x-intercept at +2 and an x-intercept at +3. Now the only one that I put the t beside was where I actually touch the graph but do not cross. Everywhere else then I know I'm going to cross. All right, I know my end behaviors had to be both up in each direction. Okay, so from here now I can go through and sketch my graph. All right, part of the nice thing about having that y-intercept here is that as I go through, and I'm going to start on the left, I'm starting here above, and my graph's going to come down. It's going to get to that first intercept. It's going to touch and go back. I'm going to have to go through that y-intercept, go to the next x-intercept where I'm going to cross. It's going to go below, turn, and cross and come back up. And then again, it's going to end in an upward direction. Does it have to be a perfect graph? Absolutely not. Could this graph actually, look something like this? Could that be a realistic graph? Possibly, okay, because I still only have 1, 2, 3 turning points, right? So that's a potentially realistic look for this graph as well, okay? But we're going to go with the simplest graph we can, all right? We want to make it as simple as possible. I want to make sure that I'm touching the x-axis where I need to, where I'm crossing the x-axis where I need to. My y-intercept is in the right place, and my endpoints or my end behavior are in the correct directions. Okay. Again, if you're doing all that, then it's also going to make sure that you're above the axis where you're supposed to be or below where you're supposed to be. All right. Make it clear that you either go above or below the axis if that's what you're doing. The one other thing I don't want you to do, right, is let's say I was graphing this and in blue here. All right. If I did something like this. Right, if you had a graph that looked like that, okay, for this part here, I'm going to look at it and say, I'm not really sure if you went above or below that axis. And I'm going to assume, and because I pretty much have to at that point, I'm going to assume that you just didn't know whether you were supposed to go above or below the axis. So please make it clear for me whether you are above or below the axis. It doesn't have to be extreme and go off of the graph, but make sure that there's no question as to whether you're above or below. Okay. So let's do another example, right? So I want to find the zeros or the solutions of this polynomial. Now this one's not factored. So let's go back and think when we talked about quadratics. What was the first thing we always looked for? Do we have a GCF? We want to ask the same question here every single time. Do I have a GCF? All right. And before I even do that, I know it's in standard form. So I have a degree 4. A is positive. So I know that my end behavior is again going to be up and up. All right. So now let's go back to my GCF. So I want to solve this In this case, I have a GCF of x squared. I'm going to be left then with x squared minus 7x and minus 18. Okay. I can factor further, right? Two numbers that multiply together to give me negative 18 and add to 7, or negative 7, are going to be negative 9 and positive 2. So what we're going to end up with then is x squared equals 0, x minus 9 equals 0, and x plus 2 equals 0. For solutions of x equals 0 with the multiplicity of 2, x equals 9 with the multiplicity of 1, and x equals negative 2 with a multiplicity of 1. I'm going to touch at 0, and I'm going to cross at 9 and at negative 2. All right. Because also I have a x-intercept that is at 0, right? I have a point 0, 0 on the graph. This is also my y-intercept, okay? And again, also think this would have been plus 0 out here as well, right? So if I go and plot these points, so I've got negative 2, I've got a 0, and I've got 9. Okay. My graph is going to touch but not cross at 0. My end behaviors are up and up. So when I go to actually sketch this then, I get a graph that maybe looks something like this. Okay. Again, I've crossed the axis where I'm supposed to. I've touched the x-axis where I'm supposed to. My end behavior is in the correct spot. And again, based on all that, then I have to also be above and below the x-axis where I'm supposed to, right? What's happening between those two intercepts, in this case where I'm below the axis, does it actually look like that? I don't know. Probably not. I would argue that between 0 and 9 for my x values, that this graph actually becomes very, very, very small, okay? But without using the graphing calculator to come up with a XY table, I don't know that for sure, okay? So this is, for what we know and what we have available to us, this is an accurate representation of this graph, okay? So we'll go through one more here. I have 3x squared times quantity x plus 2 cubed times x minus 4, and again, that's to the first. So let's find my degree, right? Degree here, sum of my individual factors powers is going to be 6, all right? And actually, let's mix it up because I feel like we've done even for everything at this point. So let's say that this was actually an x minus 4 squared. So now if I add them up, my degree is going to end up being 7. My a value is positive, and this would make my end behaviors be down and up. So already factored makes my life easy. So I have 3x squared equals 0, x plus 2 equals 0, and x minus 4 equals 0. Giving me solutions of x equals 0 with a multiplicity of 2. This is also my y-intercept. X equals negative 2 with a multiplicity of 1, and x equals 4 with a multiplicity of 1. Right? Also here at my y-intercept, I'm going to touch and I'm going to cross it. Oops, excuse me. Let me go back. Right? And I'm going to cross at negative 2, but because I made that change up there, my multiplicity here at 4 is going to be 2, and I'm going to touch at that point as well. Okay? So let's sketch this in. So I've got an intercept at negative 2, an intercept at 0, and an intercept at 4. Right? At 4, I touch but don't cross, and at 0, I touch but don't cross. Okay? I know my end behaviors have to be down and up. Right? So if I start on the left, I'm below the axis. I have to come up, cross that point. I'm going to come down. It's going to touch and go back up. Come back down, touch, and go back up. And this graph is going to end above the x-axis. Again, accurate representation based on what I know, the tools I have available to me at this point. But it might actually in real life look different than what we have sketched here. All right. We could try one more, but honestly, I think at this point it's redundant for the video. So here's another one that you guys are welcome to try. And unfortunately, it's also another even function. I need to go back and fix that. All right, so if you guys want to try that one, please go ahead, or make one up and try and solve it. All right, but if you're making one up, I would do it in factored form. Don't make something up in an attempt to factor it. It's probably not going to work very well. Now let's say we are working in the other direction. What if I know all the solutions are zeros and I want to find the function? Okay, so I want to find a function in standard form, multiply it out. Okay, of minimum degree. So if I have, 4 factors, I only want it to be x to the 4th, although technically it could be higher. All right, so if I know I have a function that has zeros of x equals -3, x equals 1, x equals 4, and I'm going to put this x equals 0 out in front for a reason. Okay, so if I have these 3 factors, or these 4 factors rather, okay, I know that x equals 0 would have come probably from, well, a factor of x equals 0, or possibly some a times x equals 0. X equals -3, if I work backwards, would have come from x plus 3 equals 0. X equals 1 would have come from x minus 1 equals 0, and x equals 4 would have come from x minus 4 equals 0. What I've now got are the factors that gave me each of these zeros. So now I want to go one step farther backwards, and I want to write this in factored form. Now, if my question had asked only to find a polynomial function, and if it didn't have the words in there in standard form, you would be done at this point. But because I put the words in standard form, I've implied I want to multiply it out. Now I must do this in a couple of steps, right? I'm going to multiply the first 2 polynomials together, and then I'm going to multiply the second pair of polynomials together. Okay? So when I multiply the first 2 together, we're going to end up with x squared plus 3x. And when I multiply the second 2 together and combine like terms, we're going to have x squared minus 5x plus 4. Now I need to distribute both terms in that first to the second. So I'm going to have x to the 4th minus 5x cubed and plus 4x squared plus 3x cubed when I start distributing the second term, minus 15x squared and plus 12x. So when I combine like terms then, we're going to have f of x equals x to the 4th minus 2x cubed minus 11x squared and plus 12x. Okay, this is now a polynomial in standard form. Okay, that gives me the zeros or solutions listed above. So I've essentially taken that process that we just did of factoring and solving, and have gone from the actual solutions, worked backwards to the factors, so I could write it as a product of factors, and multiplied it out. Okay, let's go through. Let's do another one. All right, so let's say I want a polynomial function, minimum degree, has zeros of -4 with a multiplicity of 2 and 5 with a multiplicity of 3. Notice it does not say in standard form. So again, here what I'm going to have then is with a multiplicity of 2, I'm going to have x equals -4. And with a multiplicity of 3, I'm going to have x equals 5. So here we're going to have x plus 4 equals 0 and x minus 5 equals 0. Right? When I write them then as factors, right, I'm going to have f of x equals x plus 4 quantity squared from the multiplicity times x minus 5 quantity cubed, again from that multiplicity. Okay, this would be a polynomial function of minimum degree that's going to satisfy those zeros and multiplicities listed above. So real quick checkpoint, some of these things I've talked about a bunch, and maybe you picked up some of these things, maybe you haven't, right? But if I have a polynomial p and c is some real number such that p of c equals 0. Then the following are all true statements. C is a 0 of the polynomial p. X equals c is a solution to the equation p of x equals 0. X minus c is a factor of the function, the polynomial function p of x. And x equals c, or c0, is an x-intercept of the graph of the polynomial function p. Okay? These are all one and the same, right? I could also even say that c is a root of p as well, right? Roots, zeros, solutions, and x-intercepts are all fundamentally interchangeable. They maybe just are used in different settings, one over another, okay? But they all essentially, at the end of the day, mean the same thing, all right? So let's work backwards one more time, except this time let's do it from a graph, okay? So if I take a look here at my graph, right, I've got a couple of solutions. I've got an x-intercept here at -1. I've got an x-intercept here at +2, and I've got a y-intercept at +2. Okay? I know that since I touch here, I know that I'm going to have a multiplicity that has to be even. Again, we're going to do a minimum degree, so I'm going to assume 2. Okay? So I know that I have to have the following then. I have to have a solution of x equals -1 with a multiplicity that's at least 2. And I also know that I have to have an x-intercept at 2 where my multiplicity is going to be 1. These are going to have come from factors, right? X plus 1 equals 0 and x minus 2 equals 0. And if I write this as a polynomial function, right, I'm going to have, and I'm going to put an a out in front for right now, a times some quantity x plus 1 squared times x minus 2 to the first. You might be saying, why in the world did you put the a there? Well, the a value is going to cause a stretch or compression. Right now, I can come up with a whole lot of different graphs that would satisfy, or a whole bunch of different pictures based on different choices for my value of a, right? But what I have is this y-intercept. And how am I going to use that y-intercept? I know that I have the point 0, 2 on the graph. I've got an x and a y value, or an f of x. Okay, so what I can do is substitute in, and I'm going to solve for and find a. So here, y, or f of x, is going to equal 2, equals a times 0 plus 1 squared times 0 minus 2. So here, when I go and solve, I'm going to have 2 equals a times 1 times -2, or -2 times a, and here I end up with a equals -1. So not only can I write the product of factors now with another point, whether it's a y-intercept or any point on the graph, right? I can now go back in and find the a value. I would highly recommend that you do that from the factored form rather than necessarily standard form. You can do either, but factored form is probably going to make your life a lot easier because a is out in front, it's not distributed through. So now when I go and write this, I can write f of x equals the opposite of 1, or just negative, times x plus 1 squared times x minus 2. This is a polynomial of minimum degree with the a value found that represents that graph. Okay. Again, are there other equations that I could possibly come up with that are going to give me the same result? Absolutely. All right. They might give me different a values depending on the powers that I choose, but this is the simplest and the minimum degree function that's going to give me that particular graph. Okay. One or two things more to talk about real quick. So local and global extrema. So essentially max and mins, right? I have local mins, which are what we referred to as relative mins a little while ago, and absolute mins and maxes, or global maxes or mins, right? Again, so we're looking at, a point where my function has for the local max and mins, where it has either the highest or lowest y value for the points that are generally close to it, right, that are surrounding it, right? A global or an absolute max or min then is when we have a point where it's the highest or the lowest point on the entire graph over the domain of all reals, okay, if we're dealing with a polynomial function, all right? And you can see here in the picture, right, we've got some two local mins or maxes, right, one of each, and then we have a global max, which would be the highest point on the graph altogether, all right? So the application of max and mins, right? So here I've got an open top box is to be constructed by cutting squares from each corner of a 14 by 20 centimeter sheet of plastic, then folding up the sides. I want to find the size of the squares that should be cut out to maximize the volume of the enclosed box. How in the world are we going to do that? So let's first start off. I want to draw a picture. I like pictures. I'm a visual person, right? Picture is going to go a long way here, right? So I've got something, we'll call it 14 centimeters by 20 centimeters. And I'm going to cut some squares out of this guy, okay? So I want to cut a couple of squares out of the corners. Oops, it gave me a circle. I want a square. There we go, right? And I want to cut some squares out. Oops. I want to move it. There we go. Such that we've got this, okay? So I'm cutting those portions out of my box, right? And then what we're going to do, okay, is now I'm going to so now I've got a base of my box. Okay, there we go. All right, so what I've done at this point, all right, let me zoom in and I'll clean this up a little bit. I've gotten rid of each of these corners. Okay, these corners have all gone away now. And what I'm going to end up doing is each of these sides are going to get folded up, right, in such a way that then, and my artistic skills here, right, apparently it doesn't like me. All right, we're going to fold this up into a box, okay? So what I need to figure out next, or what are the actual dimensions of the base here? Okay, I need the dimensions of the base of my box, all right? Remember, the volume of a box is going to be length times width times height, okay? I've cut squares out that are x by x squares. I don't know the size of those squares, all right? So what I'm going to try and do then is figure out the length of the base. So this 14, this side has to be 14 minus 2x, because I cut an x out here and an x out here from the original dimension of 14. And then this dimension is going to be 20 minus 2x. Okay, so when I fold this up, I'm going to have a box that's going to have a length, if you will, of 14 minus 2x, a width of 20 minus 2x, and a height of x. Now I can multiply this out, but unless it asks for it in standard form, it's really not going to help us out a whole heck of a lot. So let's go ahead, let's plug this into a graphing calculator. It's going to help significantly to have the graphing calculator available to us. So I'm going to go to y equals, all right, and I'm going to type in the function 14 minus 2x times 20 minus 2x times x. Okay, and let's graph it. Okay, so I'm getting a function, right, that I want to do. There we go. I want to manipulate this, so I'm expanding my y-axis, right, but not necessarily my x. Okay, now I can't have, right, something, I can't cut more than a 7-inch square out. Think about it. I have x-intercepts at 7, at 10, and at 0. If I cut a 7-inch square out, then I would have cut this entire square out, which means the entire length, if you will, of the box is gone. Okay, then obviously I also can't cut out a 10-inch square, right? Because I would have cut it out in the other direction completely and I would have nothing left. Okay, so I know that for this, based on my smallest dimension being 14, the absolute largest that I could cut out has to be less than or equal to 7 inches. Okay, or 7 centimeters rather. Right. What I'm actually looking for is the maximum volume. This graph gives me, it's a graph of the volume of the actual cube or box that I get once I made this cut. And if I look here, I have a local maximum. Right, my local max takes place at the point 2.7 and 339.0. Okay, so what this tells me is that I should cut 2.7 centimeter squares to get a max volume of 339 cubic centimeters. All right. So again, this is something where I'm going to use a graphing calculator for a problem like this most of the time, where I'm trying to find that local max or min. I'm going to come up with the equation. I'm going to graph it and I'm going to look for that, whether it's a local, relative, or an absolute or global max or min, depending on the context of the problem. Okay. My apologies for the fact that Notability wasn't going to let me try and draw a three-dimensional shape within 2 dimensions, at least not without spending an extraordinary amount of time here doing it. I could do it on a board a lot faster, but it was not helping. It was not working with me on the screen here today. All right. Those are the notes for 5.2 and 5.3. So the good news is, even though this might have been a slightly longer set of notes, these are the notes for 2 whole days. So your next notes day, you actually get a day off, okay, because you've already taken care of it. All right. Have a good night. We'll see you guys in class tomorrow, and we're going to do a couple of these problems together when we get here.